All right. In the last section, we talked about transmission and therefore some of the things that affect transmission, including absorption and scattering. And a natural progression from that is what we call the photoelectric effect. So this graph kind of encapsulates everything that we have about the photoelectric effect. So basically what this is we're talking about incident photons or waves and their promotion of electrons from the valence to the conduction band. And so we saw that in that last curve of showing absorption. And so that affected that. So essentially, that occurs when the energy of the wave of the light or the wavelength. So that can be represented by h times the velocity, so Planck's constant. When that's greater than the band gap. So essentially, when the energy is equal to or greater than the band gap, that means that the light can promote an electron from the valence to conduction band. So instead of temperature, the light itself is what's giving the material energy to cross that gap. And so so here we think about it in terms of energy. And so this y-axis is energy, and then this x-axis is the frequency. And so we can, by increasing the frequency, increase the energy of the incident light. And so the interesting thing about this is that once the energy of the light reaches a threshold, it promotes electrons. And so we can actually use this technique to measure the band gap of a material using light. And so that's how we can sort of do it. So in this case, again, this is showing the visible spectrum between 4 and 8 hertz here. 10 to the 14 hertz. So below that would be the infrared, above that would be the ultraviolet. And so essentially at this point, a little bit above, it looks like a little bit above 10, so 10.4 on the frequency. So that's, we can equate to the energy of the incident beam and also the wavelength. We see that at that point, the energy goes up. So effectively, that's where conduction is starting to occur. So that threshold where it starts to occur is where we know we have the energy is equal to or greater than the valence band. And so the conductivity of that material increases at that point. And so, like I said, we can use this to determine the band gap by basically doing a control experiment where we vary the frequency of light or the wavelength and look at the conductivity of that material. So that's basically what we're doing here is we're measuring the conductivity represented by the y-axis, and when the conductivity changes, that means that we have conduction increased by promotion of electron across the band gap for this intrinsic semiconducting material.